Hello again. In this video, we're going to wrap up our overview of COOL with one more example of writing a COOL program. For our final example, let's look at a program that actually manipulates some interesting data structure. So we'll begin here by opening up a file, and let's call our program list.cl this time. And as usual, we'll begin by writing our main routine and our main method. And once again, let's make this inherit from IO so we can do the IO routines here. And let's just begin with something very simple, as always. Let's just have something that prints out hello world, but in a little bit of an unusual way. We're going to end up writing a list abstraction, and let's first build a list by hand, or at least build the elements of a list by hand, and then we'll actually build the list abstraction and put them in a list. So let's have some strings. So we'll have our string hello, and this will also illustrate how you do multiple let bindings simultaneously, and I shouldn't say simultaneously, how you do multiple let bindings in one let expression. So you do them by just listing them, and notice that this uses commas as a separator rather than semicolons as a terminator. So this let binding is going to define three names. Hello, world, and new line, all of which are strings. And then we're going to now print these out on the screen. So we're going to want to be able to do outstring, and since main inherits from self, we can do that without an object there, because just again dispatches to the self object. And we want to concatenate these strings together in the right order. So we'll do hello dot, and since hello is a string, it can be concatenated to world, and world is a string, so it can be concatenated to new line, and that should do the job. And just let me point out one more thing about this these let bindings here. This notice that the comma is a separator here, meaning it doesn't come after the last one on the list. So it just separates the items on the list. It's not a terminator. And now we can close up our main procedure, close up our class definition, save it, and now let's see if it compiles. Oh, amazing. First try. And we run it, and it prints hello world as expected. So now, let's, instead of introducing the three strings separately and then concatenating them together, let's write an abstraction where we can build a list of strings, and then that abstraction will have a function within it to do the concatenation. All right, so we'll have a class called list, and every list needs, I think, to have two components. So first it's going to have the item that's in the list, and that'll be a string. And then we have a pointer to the next, to the tail of the list, to the rest of the list. And so I'll have a next field that points, or is another list of strings. And now we need a couple of methods in order to use this list. We'll need to be able to initialize a list in some way. So the initialization function will take an item and the rest of the list, the next part of the list. And what is it going to do? Well, it's going to need to set the fields of the object. And so this will have to be done as a series of assignment statements. So we'll need a statement block. And we will set the item to be the I argument. We'll set the next attribute to be the N argument. And now we actually want this initialized object here, this method here, to return the object itself, and that'll be convenient for chaining together calls to init. So we'll have it return self. It'll return the self object, and that's the end of our statement block. And then that is the end of our method. And I made a mistake up here. we have to declare the return type of init, and when it's going to return, of course, so it returns an object of type list. We need to put a list declaration there. All right, so that takes care of init, and now we can use this to build a list down here. So what should we do? Let's actually have a new variable called list that we'll introduce here in this this series of let bindings. And let's just build a list out of these three objects. So we'll say we'll have a new list, and then we'll initialize it to contain the string hello. And what should the rest of the list be? Well, that should be another list, which is initialized to have the string world. And what should be inside of that list? Well, there'll have to be another new list object, which will initialize to have new line. And now, what do we put here? Actually, there's a little bit of a problem here, isn't there? We need to put a list object here, but we don't want to allocate a new list object. We want that to be really the equivalent of a null pointer. And there's no name for that in Cool, actually. You can't write down the name of a null pointer. It's called void in Cool. There's no special symbol for that. So we'll have to create a variable that is just not initialized, and that will be, so an uninitialized variable of type list will in fact be void. It'll be a null pointer. So let's call that nil, and it'll be of type list and no initializer. And so nil there will point to nothing, or the void pointer, and then we can use nil to terminate our list here. And then we have to close off all the parens for all the nesting here. And I think that's it. And so that will be our list. Okay, so we have a list of 3 strings. And now what we want to do with that is to print it out. And so what we would like to do is to have a list call to list, and then a function that's going to flatten that list, and we'll just print it. So that is what the main program should do. And now we have to write the flatten function. So flatten takes no arguments, and it's going to return a string. It's going to return a single string. And flatten is a pretty simple function. What do we have to do? There's really 2 cases. One is if we're at the end of the string, and the other is if we're not yet at the end of the string. So let's test for that. So how do we know if we're at the end of the string? Well, if the next pointer is void, then there is nothing more in the string. And there actually is a special test for that in Cool. It's called the isVoid function, and it's written like this. So if isVoid of next, okay, so of the next field. So if the next field is void, then what are we going to return? Oops. Well, then the result here is just the item, whatever the item was in this last element of the list. And otherwise, what do we want to do? Well, otherwise we want to take the item and we want to concatenate onto it the result of flattening the rest of the list. And that is our flatten method. So let's see if that works. So let's compile this. And we got a couple of syntax errors here, so let's go back and see what's going on. So we have a syntax error here at the end of the flatten method, and we see that we left out the keyword to close a conditional. So a conditional has to be ended with fee. All right. And let's see if that's working now. And we still have the syntax error at line 29. And the mistake here is that we forgot to declare the type of this variable, which is a list. And then it gets initialized to this big expression that we wrote out. Let me just do the indentation a little more nicely here. And notice something actually is worth mentioning here, that this definition here, this definition of the variable list, depends on the definition of the previous variables in the let. So so when a let binding is made, the name, the variable that's bound, is actually available in subsequent let expressions. So in this case, this variable list makes use of all of hello, world, and new line, which were defined earlier in the same let construct. All right, let's save this and come over here and compile it. And we see we got another bug in the code. So if we come up here, we see I've made a mistake here. I've used functional notation here, calling flatten of next. And what I actually wanted to do was to dispatch to next on the method flatten. So that should be written like that. All right, probably getting close now. Let's see if it works yet. Well, it compiles. And now let's see if it runs. And indeed it does. Prints out hello world just as we expected. Now let's go back to our program and let's generalize this list abstraction in one way. Let's say that we can have an arbitrary list of objects, not just strings. And that will require us to change a few things. So it can be initialized now with an object. And now when it comes time to flatten this list, we want to produce a string. We want to produce a print representation. But not everything in the list is necessarily a string. And we need a way to traverse the list and do different things for different kinds of things that might be in the list, for different types of things that might be in the list. And so there's a construct in COOL for recovering the type of an object at runtime, and this is called the case construct. So let me first introduce a let expression here. We'll let the string that we're going to construct, which is of type string, and that's going to be initialized to something. And now it's going to be a case. And what are we going to case on? Well, it's going to depend on the kind of thing the item is. So the item in the list could be different kinds of types, and we want to do a different operation depending on what item actually is. So we'll do case item, and then the keyword is of. And now we have different branches of the case expression for different kinds of things that could be in the list. So let's say if it's an int, okay, so what this does is this says that if the item is an int, then we're going to rename it to I. We're going to bind I to that integer, and then we can do something with I. And what would we want to do with I? Well, we'd probably want to convert it to a string. So I'll do I to a of I. And what if in fact that item happened to be of type string? The item in the list happened to be of type string. Well, then we can just use the item itself as a string representation. And we could do this for other kinds of types. If we had other kinds of types in our system, we could continue to list out other cases here and how to convert them into a string representation. But let's just have a default case here. We'll say if it's any other kind of type, which would be covered by having a branch saying that if it's of type object, and we'll call it O, then we should just abort. Okay, so we should just call the abort function and quit. And that's our case. It needs to be terminated with a closing keyword called ESAC, again, the reverse of case. And now we can use that string that we constructed in our little function here. So if the next field is void, then we're just going to return the string. Otherwise, we're going to return the string concatenated with the flattening out of the rest of the list. Okay. Now there's a couple of things we have to fix up. We use the I to A method here, which means that list needs to inherit from the conversion class A to I. And there's another issue here, I see, and that's right here. So if you notice, the case statement needs to produce a string, okay? And it turns out that abort does not return a string. Abort actually terminates the program, but its type is that it returns an object. And so here we have to convince the type checker to accept this piece of code, and we need to get this branch here to type as a string. So what we can do and this is ugly, but it's the way to do it, is we put it in a block, in a statement block. We call abort first, and again, that will just terminate the program. And now we can put any string expression we want after that, and that will be that will give a type string to the entire block. So we can just put the empty string here, for example, and that has to be terminated with a semicolon since this isn't a block, and we can close that with a curly brace. Okay, so this is just something we have to do to make the type checker happy. And that may be everything we needed to do. So let's try compiling this. And we have to include the conversion library. And we have one syntax error so far. And that's because we forgot to put the semicolon terminator on each of our each of the variables that we were introducing in the let. Okay, forgot to save that. Let's try this again. And oops, I didn't actually manage to fix the syntax error, and that's because I put the semicolon in the wrong place. Actually, I forgot the variables that are bound in a let are separated by commas, but the branches of the case have to be terminated by semicolons. So what I said before was incorrect about using semicolons to terminate let bindings. It's just in case branches in this where we need it in this example. All right, anyway, coming back to this, let's see if it compiles, and it does. And now let's run it, and it works. Now, of course, we haven't actually exploited the ability to have different types of objects in the list, so let's do that. Let's add an integer in here. Type int, and let's give it the number 42. And we can insert it in here. And now we can pass any object to init in the first position. So we'll just put in 42 right there. And when we compile and run this, it should print hello world 42 if everything goes as expected. And it does. And that concludes our little tour of Cool. There are a few features that we haven't shown in these examples, but you can look in the examples directory for lots more programs, many more programs that will show you all the different ins and outs and details of the other language features, as well as the ones we've covered here.